All right, we are about to embark upon a discussion here of mass spectroscopy and how we measure average atomic masses that you're all familiar with off of the periodic table. This is Chapter 3, Lecture number 1 for Ralston Valley AP Chemistry. Let's go ahead and get started. So after last year's introductory chemistry class, we are all very familiar with the concept of an average atomic mass, those values that are reported in the upper right-hand corner of each little elements box on the periodic table. We're going to take a quick moment here to talk about how we actually measure those average atomic masses. And after that, we'll talk about some kind of nuances that we didn't get into much last year about the measurements that we make and as always, gain an understanding about how the world is a little bit more confusing than we initially thought it might have been. So, first off, if we want to measure an atomic mass experimentally, we're going to use a device called a gas chromatography mass spectrometer, or a GC mass spec for short. This tool is a tool that chemists use to very, very accurately separate particles by their masses and determine the relative abundance of the different isotopes of each of the different elements. You might remember back to last year when we were doing the Vegium lab, in which you calculated the average atomic mass of that made-up element Vegium, the beans and peas and corn mixture. In making that calculation last year, we went through and individually counted particles of peas and corn and beans to determine the relative abundance of the different isotopes of that element Vegium. Now, obviously, to do that with real-world atoms, that's a much, much more complicated scenario. First of all, because we would be counting literally billions of particles. And second of all, because each of those individual particles is so small that we can't really just collect them individually with tweezers or something and pull them out. So instead, we use a clever device here, which we again call the gas chromatography mass spectrometer, which is diagrammed here on your page right now. The key idea of the function of the gas chromatography mass spectrometer is this. We start by injecting a sample into our oven, and that oven heats up the sample of matter to a very, very high temperature, moving everything into the gas phase. So we've got a little heating coil present here on the left-hand side in red here. And after that sample is heated up to very, very high temperatures, it is then injected into what's referred to as the ionization chamber. In that ionization chamber, those gas phase particles are subjected to bombardment by essentially an electron gun. And that electron gun is just a stream of particles, and when those electrons strike the atoms inside of that chamber, they can knock off other electrons, creating positively charged ions within that chamber. Now, those now positively charged gas phase ions are ejected from the chamber at speed and pass across a magnetic field. Now, recognize that if you've got a positively charged ion which is moving through space, what you have then is a moving charged particle, and from your physics days, you recall from your laws of magnetism that moving charged particles generate themselves a magnetic field. So if we have an external magnet present here, and that moving charged particle itself exerts a magnetic field, we would expect to see those magnetic fields interact with one another, and that causes the beam of positively charged ions now to deflect. And there's a little detector screen that's off to the side there that then picks up where those different particles strike the detector screen. And the key idea that allows us to use this tool to separate particles by their mass is the idea of inertia. If you imagine driving your car down I-70, if you're driving a little tiny light car and a big huge gust of wind comes up from the side and blows on your car, that car's pathway will probably be deflected to a larger degree than if you had a much, much more massive car hurtling down the highway at speed. And as such, we can infer the masses of the particles by recognizing that the degree of deflection of their path is proportional to the particle mass. And by taking into account the number of times those particles strike the detector screen at each one of those different deflected positions, we can get a measurement electronically of the relative abundances of the different isotopes that were present inside our sample of matter. So this tool allows us to simultaneously both calculate the particle masses as well as the relative abundances of those different isotopes in our sample. So now that we have had a look at the workings of that machine, the gas chromatography mass spectrometer, let's next take a look at the readout that we would expect to see from using such a device. You'll notice here on the right-hand side, we've got a graph here, and this graph essentially is an idealized version of the signal you would get from using the mass spectrometer in order to measure the relative abundances of the different isotopes of neon. And you'll notice that on that readout graph there, we end up with 3 peaks along the graph there, corresponding to mass numbers at a mass number of 20, 21, and 22. So remember, this is all neon, so all of these atoms have the same atomic number, which really means that what we're seeing here is differences in terms of the isotopes that this mass spectrometer is picking up for neon that have different number of neutrons. And you'll see there that the peak corresponding to the mass number 20 is significantly larger than the peaks corresponding to 21 or 22. And what that really tells us is our detector screen picked up way more strikes of neon 20 than it did of either of those other isotopes there. That is, neon 20 is a much more abundant isotope than neon 21 or 22. And you can imagine simply going through and integrating to find the area under each of those curves, and that would give me an idea about the relative abundance of those different isotopes compared to one another. So understanding what the sort of readout we get from a mass spectrometer now, let's go ahead and take this data and make a calculation to determine the actual average atomic mass for this element. So follow with me through here on example number 1. We see here that we've got data from that graph there of the relative abundances of neon. And again, just like we see on the graph, it appears that neon 20 is significantly more abundant than neon 21 or 22. With 90.92% of all those isotopes showing up on our mass spectrometer corresponding to neon 20. And from this data, we want to go ahead now and calculate the average atomic mass of a neon atom. Now, calculating the average atomic mass is essentially calculating a weighted average. Just like if you were to calculate your GPA for a semester and you saw that that semester you had got 5 A's and 1 B, your average of your grade point would be closer to that of a that is closer to a 4 than it would be to a 3 because the A was a more abundant grade which you received on your report card that semester. And in a similar fashion here, we would expect to see our average atomic mass of neon be closer to 20 than 21 or 22, because in our example, neon 20 is by far the most abundant isotope of neon. So essentially what we're going to do is calculate a weighted average here. And we can do that by converting these percentage abundances for these different isotopes into a relative abundance, that is, into a decimal, and then multiplying that relative abundance by the mass number for each of those isotopes, and then simply adding up all those values to determine the overall measurement of the average atomic mass. So follow through with me here as we do that. This is a skill you learned last year, and we're just refreshing real quick. We're going to convert 90.92% into a relative abundance, that is parts out of a whole. We would get 0.9092 by moving that decimal place 2 to the left. And we're going to multiply that by our mass number of 20. Adding to that the contribution from neon 21, again, make sure to move that decimal place 2 to the left to convert this to a relative abundance. 0.00257 multiplied by the mass number of 21, and the same thing for neon 22, 0.0882 times the mass number of 22, and we simply sum up each of those individual contributions to our overall average atomic mass, and we end up with a value which is 20.17837 by my calculation. Now, that seems rather reasonable, especially when we compare it to the periodic table, where we find a value given on the periodic table for the average atomic mass of neon of 20.1797. Now, that being said, note that there are some differences between our calculated value for the percentage abundance and for the actual value reported on your periodic table. And before we just go ahead and chalk all of that up to just a difference in significant figures, let's think about some of the reasons why our value might not exactly agree with the reported value off of the periodic table. And one first reason we might come up with would have to do with sampling error. Even though our sample of neon has an enormous number of neon particles, like in the billions of particles, we would expect to see sampling error to be relatively small with such a large sample size, but where that sample came from is important. Our sample might have come from a place which was particularly rich in a certain radioactive element, which would have led to a disproportionate number of one or more different types of those isotopes being produced at some point. And that might not have been the case in other places in our universe where we would sample from, which means that, yeah, from sample to sample, we would expect to see meaningful differences in terms of the average atomic masses measured for those different elements when we're getting down to very accurate measurements and lots of sig figures. But there's something even weirder than that going on here that we'll discuss next on the follow-up slide. So sample error, one thing to watch out for, but let's look out for something extra weird coming up next. Now, we just mentioned on that last slide that our value we calculated for the average atomic mass of neon doesn't exactly correlate to what we would have seen on the periodic table, and we hypothesized that one of those reasons might have been due to a sampling error. But there's something else going on here as well that we need to consider, and that is when we are talking about the mass numbers of the different isotopes are not actually whole number values. And that is due to a very weird little quirk of how our universe works. We taught you last year that the mass of a proton or a neutron is 1 AMU, and that's relatively mostly true. But the problem is that the mass of a proton or a neutron, as it turns out, is not constant because of an idea we discussed a couple of units ago from modern atomic theory. Recall that from Einstein's equation, E equals mc squared, energy and matter are really interchangeable ideas. That is, matter is really just one form of energy. And as such, when we take protons and neutrons and place them close to each other, that changes the potential energy of those protons and neutrons relative to one another. And because mass and energy are interchangeable, what that really means is by changing the neighborhood around a nucleus for how many protons and neutrons there are, we can actually change the potential energy, which means we also see slight changes in the actual masses of those particles as their potential energies change. So long story short is, the mass of a proton is not a constant value. It varies depending upon the potential energy of that proton. And because of that, we need to have some sort of standard that we can compare to when measuring these atomic masses. Otherwise, we would really have no idea what we really meant when we were talking about a mass of 1 AMU. And so for a long time, the standard that we have used is the standard of carbon-12. That is the isotope of carbon with 6 protons and 6 neutrons. By definition, we define the mass of the nucleus of carbon-12 to be a mass of exactly 12 AMU. And so once we've defined that point, we can then compare all other masses of nuclei relative to carbon-12, recognizing that they're going to change in terms of the mass per proton or per neutron, depending upon the potential energy of the various nuclei. So we've got a standard to which we compare everything else against, but that really means that the mass numbers of all the other isotopes that we deal with really aren't whole numbers, except for that standard carbon-12. They're going to be close to whole numbers because the changes in potential energy are not very great as we go from one nucleus to the next. But yeah, they're meaningfully and measurably different from what we'd expect as whole numbers. So again, because the mass of a proton or neutron varies and changes depending upon its potential energy, that means that the masses of all the different isotopes really aren't whole number values. So in your book, when you're doing some of these problems, they might actually give you the actual measured mass numbers of the different isotopes, which will again not be whole numbers like we used in our example on the last page. So, yep, the world's a weird place. A proton doesn't always weigh what a proton weighs. And that's something we just have to come to terms with in terms of how the universe actually functions. So, one other thing I want to note, just as a quick reminder, and this is an important thing when we go forward into our calculations involving stoichiometry, the calculation we have just made is a calculation of the average atomic mass in units of AMU of a particular element. Because of the relationship that exists between that concept of Avogadro's number and mass, the masses that we're calculating here, in addition to being average atomic masses of the different isotopes in units of AMU, are equivalent to that element's molar mass measured in units of grams per mole. So these calculations are going to be meaningful moving forward when we get into our mole map problems in our next unit. So that's it for our discussion of average atomic mass. I hope you enjoyed, and we'll see you in the next lecture.